Well, welcome to our Honest Investigators Talk Shop show. I'm your host, Doug Bundy, president of the Larson Research Center, where we are unveiling the universe of motion. Today is Saturday, February 27th, 2016, and we're sure happy to have you here. In parts 1 through 3 of this series, we've presented a general overview of the work, the purpose of the LRC, Larson Research Center, and I'm just checking to see. I don't see any indication that the audio is feeding through, so I hope it actually is. Darn. But this thing should give me some kind of way to monitor it, but I don't have that. At any rate, it looks like everything is coming through all right. Looking at other ways. So as I was saying, we've shown the purpose of the LRC as well as the major acronyms that we employ, and there's a lot of them throughout these lectures. So please refer to the videos of those previous lectures for orientation type information. Now, this is, again, the seventh in the series in this lecture 3, the seventh in the final series. In presentations 4 through 6 of the series, we've explained what we might call 7 major achievements of the LRC's RST, Reciprocal System of Theory-Based Physical Theory Development. All of these videos are available on our YouTube channel as well as on our website, which are all entitled LRC Physics. If you go to our website at lrcphysics.com and click in the left-hand menu there, it says online lectures, and there are all the lectures really that we've had since we did these live lectures in Clearfield, Utah, as well as lectures by other people that we think are important. So right up to the last one that we did last week. So check out our website. There's lots of things to discuss there. And then come here for the live presentations on our YouTube channel. And or I think you can even watch it on Facebook. But here on our YouTube channel, you can comment. So the comment section there should be open, and you can submit questions and so on like that. Well, in our last, like I said, in our previous lectures, we've explained 6 major achievements of the theory of motion. And let me see how we would list those as shown here on this chart. I was just checking to see that I had advanced the chart. It looks like everything's okay. All right, so assuming you can hear me now, our first one explains how the physical universe consists of 2 reciprocal sectors, the material and cosmic sectors. This is due to the nature of motion, that where the progression in 3 dimensions of the motion produces a unit motion, where 1 unit of space progresses for every unit of time, and that is identified as the speed of light. So you have then entities that form that are less than the speed of light, and then those that are greater than the speed of light, which of course is not really recognized by what we call the legacy system of physical theory, the mainstream physics that are the main endeavor of the Gentile nations. And of course, if they, in their theories, if they have anything that's greater than the speed of light, they call it a tachyon, then that automatically invalidates the theory, because they understand Einstein's theory that nothing, no matter can go can actually have a relative speed greater than the speed of light. And of course, that's true, but that doesn't mean that there aren't entities that aren't matter that can form on the other side of that boundary. Well, and so that's the first major achievement. It doubles the universe, so to speak, and explains a lot of phenomena, astronomical phenomena, that otherwise is inexplicable, as we will someday hopefully see. And then the second achievement explains the origin of light as discrete entities of scalar motion combinations, known as photons, of course, propagating at the speed of light relative to matter. Now these we've shown how these combine automatically, or I wouldn't say automatically, but the probability of these combinations forming is quite high because of the orthogonality of space and time progressions. So these turn into oscillations. Now we can't explain how the oscillations start, but because it's possible, then anything that's possible can be. So is that how we express it? It seems like we can express it better than that. But anything that is possible, and I can't remember exactly. Anyway, the fact is that because it is possible to happen, then it's going to be somewhere in the universe. It's going to exist, and then that also then explains the origin of matter in terms of combinations of these scalar motion entities, and these combinations are found in the standard model of particle physics that classifies the particles that have been observed in the last 50 years, 100 years, that we call quarks, and those are the fermion, the leptons, and the quarks are fermions. And then we have another class of particles that are bosons, and they have various distinguishing properties. And the fermions form these quarks, and each quark has its anti-quark, and each lepton, which is an electron or a positron or a neutrino or an antineutrino, these have their antiparticles. So the antiparticle of the electron is the positron. The antiparticle of the neutrino is the antineutrino. And then, of course, you have the up quark and the anti-up quark and the down quark and the anti-down quark and so on. So all of these are formed. Now, there are three families of those, and but only one family is stable. So we just deal right now with the one family that is stable, and then as we get to the point where we can deal with the other two families, maybe we will do that. But that's important then to understand. Well, now that's a third achievement. The fourth great achievement of our theory is that it explains how these entities have the correct properties of observed quarks and leptons, which can then combine in the proper way to form protons, neutrons, and electron constituents of atoms. So they form first protons and neutrons out of the quarks, and then the electron can join those combinations and form atoms. And then that's the fourth achievement. The fifth achievement explains the chirality of the standard model entities. And that means the left-handedness and the right-handedness. That's all in this. It all comes out in the combinations of these photon-like ST units, we call them, space and time units. To find more details or to understand the detail of this stuff, you can refer to our previous lectures. But the important thing about the chirality is that it enables us then to make the sixth achievement, which explains beta minus and beta plus decay in terms of conservation of motion. And that was pretty exciting. That was a recent development And we talked about that in our previous lecture last Saturday. So now we want to move on to our next achievement, the theoretical development of the or not the development, but the calculation of the atomic spectra, starting with hydrogen. You know, the theoretical development of the LST, the Legacy System Theory Community's quantum theory, that we call it quantum physics. The theory behind that started, of course, with the discovery by spectroscopists. That's a difficult word to say, but those that specialize in spectroscopy, or the study of light. And it started when they discovered that atoms of different elements absorb and emit photons of discrete frequencies and intensities that are characteristics of those atoms. For example, hydrogen's characteristic pattern of distinct frequencies shows 5 lines in the visible spectrum, 5 discrete frequencies of light in the visible spectrum that are now named for Johann Balmer, who first managed to formulate an equation to explain these phenomena. And soon after that, Johannes Rydberg was able to reformulate Balmer's equation to make it generally applicable to the atomic spectra of all elements. That was a great breakthrough, and that and other developments, especially Rutherford's results of his experiments, quickly led to the proposed model of the atom, which is composed of a nucleus of protons and neutrons surrounded by orbiting electrons, with the distance of their orbital paths determined by the absorption and emission of photons, something that any high school physics student knows all about. And those photons that are absorbed and emitted are of a specific frequency, as I said, and that frequency is indicated by the pattern of their spectral lines. And hydrogen has 5. Let's see, forgot to change to our next slide there, and I'm talking about it. But these hydrogen lines are calculated using their frequencies, their wavelengths are calculated using the Rydberg equation, which is interpreted in terms of the atomic model known as the Bohr model, the model that's named after the famous physicist Niels Bohr. And that's where the nucleus is surrounded by orbiting electrons. Of course, the subsequent development of quantum physics theory invalidated the Bohr model in some respects, but it continues today as the only accepted model of the atom capable of explaining the atomic spectra that you see here, the red line at 656.3 nanometers, and then this bright green line, or maybe cayenne line, I can't remember the name of that color, 486.2 nanometers, and so on. Right on. Now, there was another one that wasn't visible that we're going to be talking about here yet, but it forms what they call the Balmer series, and he was able to calculate all 6 of them, these 5 and one more that he didn't even know had been discovered, by using the things that he a constant that he discovered by trial and error, and also some rational numbers that he discovered based on the squares of 1, 2, 3, and 4, so on like that. So this resulted then in that Bohr model, and it's still used today, even though it's known not to be accurate in some respects. So Dewey Larson, though, the author of the reciprocal system of theory, rejected the entire structure of the Bohr model, as he explained in his book, The Case Against the Nuclear Atom, and it's a strong case. In his RST-based model, the electron becomes an integral part of the atom, and what is thought of today with the Bohr model as the nucleus of protons and neutrons is actually the atom itself in his model, consisting of a combination of scalar motions identified as protons, neutrons, and electrons separately, but which lose their individual identity as constituents of the combinations that make up the scalar motions identified as atomic elements. However, Larson was never able to explain in his works how photons were absorbed and emitted by the atoms of his model. And a university professor from India, K.V.K. Nehru, who seemed to be the heir apparent of Larson's work in the early 1980s, later, after Larson's passing, declared that calculating, quote, calculating the electronic energy levels should be our immediate priority. That is the society of RST devotees, of Larson devotees, because with this glaring lacuna present, referring to this lack of being able to calculate the atomic spectra, the reciprocal system cannot gain acceptance. Close quote. This was written in his August 2002 paper that was submitted to the and presented to the International Society for Unified Science, as it was called, and his presentation is called the Quantum QM Approach. Is the QM Approach Inevitable? Was the name of his paper. Well, you can see the problem here in this chart, where the Bohr model has nucleons surrounded by moving electrons. The Larson model, the RST's atomic model, has atoms with internal combinations of scalar rotations that he describes as one-dimensional, two-dimensional, and then three-dimensional rotations. But so it's completely different in the way it works. Electrons confined to orbits defined by energy of absorbed and emitted photons is an important part of the Bohr model and enables them to calculate the spectra so easily. But over on Larson's model, combinations of these scalar motion rotations existing inside of what he calls unit space, which is the time region, and we won't get into, but it introduces very unusual effects because of the change of the nature of the magnitudes that are inside that time region. So it makes it much more complex. It's nothing as simple to explain nor to use as Bohr's model. And then on the other hand, in the Bohr's model, the energy of absorbed or emitted photons follows the Redbirds equation for hydrogenic atoms, that is, atoms that are all ionized down to one atom. Then they can do this very easily. When you get more than one, I'm sorry, I always make these mistakes. I meant electrons that are ionized down to one electron. They call them hydrogenic atoms, meaning they're like the hydrogen atom that has only one electron, because as you get more and more electrons with these more complex atoms, then they shield one another and it makes it difficult. So they've never been able to solve what they call the wave equation, Schrodinger's wave equation for these higher atoms, because of the lack of clarity due to the complexity that gets involved when you use the wave equation and you have so many electrons whirling around. So, on the other hand, in Larson's model, the atomic thermal energy and ionization level of the atom accounts for this spectral absorption and emission, but that too is difficult because so many variables come into place. So that's never been solved. Larson, in trying to do that, finally gave up and went on because he didn't want to be, and we're glad he did. He didn't want to be held up by trying to calculate that. But on the other hand, we have had the liberty to work with it for years, and so we've done so. But then the next thing, of course, on the Bohr's model is that using that Rydberg equation for hydrogenic atoms, these levels N1, N2, and so on, as we've seen in the previous graphic here, these different levels here are easily calculated using the Rydberg formula. So it has actually been the foundation of quantum physics. It's just amazing. Even though, as I said, they know that electrons don't have the spin that people talk about them having, and they don't really orbit in these orbits that are shown by this graphic here. But nevertheless, it has been the foundation of quantum physics. But on the other hand, for Larson's atomic model, those levels have never been verifiably calculated, and therefore the RST science really hasn't been founded in that way, and that makes a big difference. Well, now Nehru's idea was to solve this problem back in 2002, was to admit that vector motion wave equation, the Schrodinger equation of the LST community, could actually be used, after all, in a scalar motion model of the atom, which he envisioned as consisting of an atomic zone and a nuclear zone, which he posited to exist in an unusual region of space and time defined by Larson's work, which resides within the unit of space, and they call that the time region. However, the vector mathematics of Nehru's approach was way beyond the reach of other RST researchers, and anyone trained to deal with that mathematics and those complicated equations was usually disinclined to follow the unorthodox ideas of Larson after having invested so much time and energy in the LST approach, in the Bohr model of the atom, and the Schrodinger wave equation, and all of the things that went into calculating the various energies and things that consists of quantum mechanics. Well, that's the reason then that this suggestion of Nehru's never really caught on among Larson's devotees, and the progress of that research ceased from that point on. And since that time, however, Ronald Satz, another heir apparent of Larson's work, claimed to have found the solution to calculating the atomic spectra without actually specifying an RST based atomic model alternative to the Bohr model in any other terms than what Larson had. And Larson never really got down to the specifics, or, well, he did. He got down to specifics, but they're very complicated concepts, and they have no way of being verified. And they don't. There's nothing in Larson's model in terms of individual electrons. So in this extension, though, of Larson's approach, trying to really finish what Larson started, Satz derives equations from Larson's theoretical development, and those are then employed to calculate atomic ionization energies, which supposedly conform to observations of atomic spectra. But with the use of such unorthodox concepts and the unfamiliar notation that he uses and in great quantity, it becomes impossible to follow the development with any degree of certainty without spending an inordinate amount of time and energy to understand what it is that he's trying to say. So the progress then, as a result of all this, the progress of the theoretical development of the universe of motion remains stagnant, and the progress of the reciprocal system of theory remains stagnant. But that's about to change, I think, if what I'm going to present in this lecture is valid. So we will continue then with kind of understanding what it is that well, I kind of lost my train of thought, but basically we're now able to show how the energy levels of hydrogen atoms simply follow the levels of sequential boson magnitudes of photons as they are added to the magnitudes of the three ST units, S pipe T units of the fermion electron without changing their S pipe T balance. Now I know that's a word, that's a mouthful, but the fact is that we need to understand that really applies to this previous slide here. The atomic spectra of hydrogen is easily calculated using the Rydberg formula and our new model, RST-based model, we call RS small t atomic model. And the calculations emerge from the consequences of the fundamental postulates of the RST, and those combinations of scalar motions expressed in terms of the motion equations of the new scalar mathematics that we've introduced with that conserve motion in their symmetry. So that's an important point that should be emphasized. And then the scalar motion magnitudes of these photons absorbed and emitted by the electron in the hydrogen atoms follows the Balmer-Rydberg quadratic sequence exactly. That's what we're going to show. I don't know what happened. I somehow lost my place there and skipped that slide. But that's if the bullet points on this slide hold up, things are about to change. So we're going to start now with what it is that Balmer accomplished. It turns out that the Balmer equation, which Rydberg rearranged, developed from multiplying a sequence of unit rational numbers, the denominators of which are displaced by 2 squared times, and then multiplying that times a constant that he obtained by trial and error. See, this was his original thing. Here he saw that this fraction multiplied by his constant, which he called h, later had to be changed to b for Balmer in order to keep it from being confused with h used for Planck's constant, would give one spectral line, and then this fraction times the constant would give the next one, and so on and so on. So for these 4, he was able to show, and of course, since these are fractions, he could see that this would be actually 3 squared over 3 squared minus 4, or 9 over 9 minus 4 is equal to 5. And this one then would be 4 squared, or 16 over 16 minus 4, which is 12. The same thing there, you see, times the constant. And then this would be 5 squared minus 5 squared minus 4 again. So that would be this fraction here times this constant, and so on for the next one, which is actually 6 squared over 6 squared minus 4, which gives us this fraction, which is equivalent to that fraction, times this constant, would give us the proper line there. Now it was amazing. So it was actually the wavelength of those line spectra, lambda, that would be calculated by multiplying the constant, and nobody knows how he really got that constant, by trial and error, times m squared over m squared minus n squared, where m squared is 1, 2, 3, 4 squared and n squared is actually just a constant 2 squared, or 4. So you see how he was able to formulate the equation there, so that lambda, the wavelength of that line spectra, is equal to his constant b times the number squared over the number squared minus 4. And so that was, he published that just as Rydberg was about to publish something very similar. But this enabled Balmer to calculate 5 visible spectra lines of hydrogen, and then even another invisible one that he hadn't yet heard about, but had been detected by someone else. So in this equation, though, is really interesting because of this number 4. Why does the number 4? That caught my attention immediately, because as those of you who have been following this series of lectures knows, the number 4 is the lowest number of units of scalar motion forming the ST unit, the first ST unit that can be formed, which we identify with photons in our theoretical development of theory. Our fascination with the number 4 even goes back to the Greek tektactris, which is based on four levels of dimensions, which match the dimensions of Larson's cube. Remember, which has the point, the lines, the planes, and the cubic volume. So there's 4 magnitudes there. So we have 4 dimensions, counting 0, and we have 4 magnitudes, counting the point. And so now here we have this fundamental magnitude of our theory showing up in Balmer's work, and he didn't know why. He just discovered by trial and error. And we know that it's the total motion in the equation for the fundamental ST unit, S pipe T unit, and the number 2 squared, or 4, shows up in the calculations then of Balmer's atomic spectra. That's just amazing. And I have to say, I was highly intrigued when I saw that and wondered whether there could be a connection. And it turns out that there is. But before I explain why, we need to understand this next chart, this next slide here, which shows what Rydberg did with Balmer's work, noticing the number 4. It turns out that what he did was divide Balmer's constant into the number 4, and that gave him the Rydberg constant here. This has come to be called his Rydberg constant, his constant named after him, the Rydberg constant for hydrogen. And the others are, there's another Rydberg constant that is slightly different than the hydrogen one, but not by much. But he got this one originally from Balmer's work by dividing the number 4 by Balmer's constant. And that gave him then, because of the inverse, because it turns out that Balmer, well, I'll explain in a minute, but that gave him the inverse of what Balmer had, which was the wavelength of those hydrogen spectra. And so what Rydberg's constant was equal to was 1 over the wavelength. And so it turns out then that because if you multiply Balmer's constant times Rydberg's constant, you get the number 4, which makes all this possible. So now Rydberg's is equal to 4 divided by Balmer's, and Balmer's is equal to 4 divided by Rydberg. In one case, it's the wavelength that is the result, and the other is the inverse, or what they call the wave number. This is the wavelength, and this would be the inverse of the wavelength, or called the wave number, the number of waves that can fit in the wavelength. So as a result, then the dimensions, of course, of Balmer's constant are nanometers. That's important. So it's the space dimension being wavelength, and so when you divide his constant by 4, his constant's about almost 300 well, it's approximately 364.5 nanometers. Divide that by 4, and it gives you 91 point some odd nanometers, which is actually the wavelength of the ionization energy for hydrogen, the limit. This was extremely important. And it follows that this magnitude then has to be the inverse of Redbirds constant, which is 1 over the Redbird constant is 91 point. That limit, that ionization energy limit, is the inverse of Redbirds constant, which is 109.73731, or mostly expressed as 1.0973731 times 10 to the 7th power. So that's a large number, and the inverse is a very small number. But isn't that amazing that the inverse is the actual ionization wavelength of the energy required to ionize the electron? And that's because of the way Balmer went about discovering what he discovered and what Redbird did with it. All right, so he took the number 4, and as a result, we get this amazing relationship between these two constants. But what if this number, before I go on, have I not been, okay. So in this next slide, we can see Redbirds constant, the result of it. Again, Balmer's times Redbirds constant is equal to 4. But if you take his constant, then he was able to manipulate the equation of Balmer and come up with this equation where 1 over the wavelength was equal to his constant times 1 minus 1 over the square of the level that you wanted to calculate. So if you wanted to calculate, remember, Balmer had to start with level 3 when he first started out. But because of Redbird's insight, he was able then to rearrange the equation and come up with this, which shows that the difference between 1 and the inverse of the square of the level you're looking for would give you the wavelengths as shown here. And again, it shows what Redbirds constant is actually 1.09. They use 6.8. I copied this from Wikipedia, which doesn't exactly agree with what's on Google, but like they said, it's approximate. But anyway, then that gives us an energy level, ionization energy level of the electron, which is 13.6 electron volts divided by Planck's constant times the speed of light. So that would give us then Redbirds constant. Now that, you see, all these relationships are really, really interesting. And again, it became the foundation of what we call quantum physics today. So the result was that you could, once he had rearranged the Balmer's equation like this, then you could take any level and calculate the wavelength of energy of the transition of the electron. So if we're going from level 2 down to level 1, then that would be the wavelength of the light, the photons would that were emitted would be 121.5 nanometers. If you're going up a little higher and coming down to 1, then it would be this number, and so on, each one of these numbers. And finally, the infinite one of what they call the Lyman limit, because this is the Lyman series, then would be 91.13 or so. That varies depending on the value of this Redbird constant, nanometers. So as a result, then we have this tremendous and mysterious relation between these two constants, Balmer's and Redbird's, and the number 4, which really to no end. Again, here you can see Balmer's series starts with 3 and 4 and 5. That's the original one he started with there. So at any rate, it's important to understand that this number 4 and how it relates. Well, let's take a look at it then. If we um, recall that the equation of our fundamental ST unit is S pipe T is equal to 1 over 2 plus 1 over 1 plus 2 over 1, and that totals the 4 pipe 4. And remember that the reason we use pipe in one instance and the division symbol in the other is because we have these oscillating units on either side. And those now are plotted over here with, as we've shown before in other slides, with time progressing upward in the vertical axis and space progressing in the horizontal axis in this direction. And then we get reversals after 1 unit here. In the case of the space component, it oscillates in 1 cycle over 2 units of time, right? So that gives us a space oscillation of 1 over 2 units of time, where the 1 here is not a count of space units as we're normally used to in this equation here, but it is actually just indicating 1 cycle. So 1 cycle would be in 3 dimensions would be a collapse to a point, and then an expansion to a ball, and then collapse and expansion, collapse and expansion. There's 2 parts of that cycle, 1 down and 1 up, if you will, and that's clearly analogous to what you have in rotation, right? Because when we rotate from 0 to 180 degrees in one direction, that's 1 unit of pi. And then as we return to the starting point, we rotate in the opposite direction. Actually, you can consider it the same direction, just as this is the same direction in time, but actually there's a reversal in the rotation because you're going from top to bottom, let's say, and then in the next half you're going from bottom to top. And so that takes 2 units of time, but we call it pi radians. So it would be 1 cycle per 2 units of pi. So we describe rotation as 2 pi radians. And that's the same thing here. We can see that in both instances, that here it's time that's collapsing and expanding, collapsing, and so on. And it takes 2 units of space for each cycle to do that. So we have then S in that sense equal to 1 over 1 cycle every 2 units of time, and T then 1 cycle in every 2 units of space. And that's important to understand because we're trying to relate our scalar motion equation to the well-known equation of energy that is used in the legacy system of physical theory, where E is equal to h, which is Planck's constant, times nu, or the frequency that's measured in cycles per unit of time of the radiation. And so dimension-wise, that's the same thing as saying, all right, the energy with dimensions T over S is equal to T squared over S times 1 over T, which is then this artificial configuration, if you will, of cycles per unit time. So that is very easy to do if we consider these equations not as this normally would be 1 unit of space, that 1 unit of space that goes first, in this case, increases over time. And well, actually, because of the arrows going down, we'll say this unit of space, after having increased in the previous cycle here, where both time and space were expanding, then this decreases while time continues to increase. And so we get the oscillation. So that's what that is showing, accounting for all these cycles of motion. 2 cycles, 1 plus, not cycles, let me say units of motion. So that really we have 2 over 2 in the horizontal, on the vertical, and 2 over 2 in the horizontal, which gives us 4 altogether. You can see that, right? I mean, sometimes it's difficult for me to explain everything, but then we can interpret this as a cycle, 1 over t, in this case for energy, in another sense where the 1 isn't 1 unit of space, but 1 cycle, which in our case is actually 2 units of space, but they are reversing. Anyway, I hope that makes sense, because it's really important to understand that. Now, in our next slide, we see the results of this. And this is going to be important, very critically important to understand, that by dividing an S cycle by a T cycle, which are, of course, inverses of each other, it produces the square of the magnitude, or the inverse square if the T cycle is divided by the S cycle, as shown in this slide for 6 magnitudes of ST. So see here, the T cycle is the time cycle is actually divided by the space cycle, and of course to divide one rational number by another, you invert it and multiply it, so that gives us 2 times 2 squared over 1, and so the magnitude there of that relationship is 2 squared, where we have this time cycle or space cycle. It's easy to get it mixed up. This is actually a space oscillation giving us a time cycle, if you will, and this is a time oscillation giving us a space cycle. So you can see if we divide, see, and then I got them mixed up even. So whatever, but the point is that the one is oscillating in space over time, whatever you call it, and the other is the reciprocal of that with time oscillating over space. So if you divide this one by this one, you get 2 squared. If you divide this one by this one, you get 3 squared, and so on, 4 squared, 5 squared, 6 squared. If you reverse those, of course, then you get 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 5 squared, and 6 squared. So as the magnitude of these cycles increases, then you get this result. Well, now that is extremely important, and the motivation for performing this division operation is not all that clear at this point, but the fact that the S and T cycles are inverses of each other implies that they go together as such, since once this operation is allowed, everything falls into place, as this next slide is going to show. So let's go to the next slide. And I know it looks complicated, but it's really pretty simple. It's very busy, but it's going to explain everything, I hope, everything about our S-pipe T periodic magnitudes, all right, that are expressed in terms of these cycles. So over here on the left, we see what happens when we add those. In our first fundamental ST unit, we have 1 cycle of space oscillation combined with 1 cycle of time oscillation, and that then gives us, as we just saw, if we divide the red here by the blue, that will give us 1 over 4, which is 1 over 2 squared. And same thing with now when we add 2 of these together, so that we have 2 what we call space units and 2 time units, or what we in previous lectures have shown to be symbolically represented by green, the color green in the middle of red and blue, a line of red on one end and blue on the other end, to try to keep all this stuff straight. We have 2 units, so that would be, instead of 1 over 2, as in, let's see, as in this equation right here, this would be just the fundamental, the first fundamental, if you will, equation, S pipe T equation. Then if we double that, this becomes 2 over 4, and this becomes 4 over 2, and this becomes 2 over 2, and then that is equal to 8 over 8, or 2 times 4 pipe 4. And we've shown that in our lectures, how the mathematics works wondrously like that. So that's what we're showing here, but we're showing it in terms of the plot of these things. So here's 1 over 2 on this end, and 2 over 1 here, and then we go to the next one where that doubles. We have 2 units of space oscillation, and combined with 2 units of time oscillation. But notice that the cycle now covers 2 units, where here it covered 1 unit. Now I've made these smaller because as if there was 3 dimensions here to look at, but they're all actually all the same. I was just trying to fit them all on one page. So you see there then that the cycle of both, the space oscillation now has a wavelength, if you will, a cycle length we could call it, because this is a 3-dimensional oscillation. It's not actually a wave. It's related to a wave, but you see it's 2 units to collapse, 2 units to expand, constituting 1 cycle, and then 2 units to expand and collapse, and 2 units to expand for the second cycle, and so on. Same thing here with our time oscillation, only this time it's space, remember, is expanding out to the right. So we have 2 units of space oscillation to expand from 0 to full 2 units of space, and then over 1 unit of time. I'm sorry, over 2 units of time. This is 2 units of space over 2 units of time, and this is 2 units of time over 2 units of space, the oscillation. And then in the next one, we add another one, a third one, and now that length changes to 3 units in both space and time. So 3 units to collapse, 3 units to expand, 3 units to collapse, and so on. 3 units to expand. I couldn't put it all on there. It's truncated. But then when we go to 4, it's the same thing, right? Now the length is 4 units to expand, 4 units, 4 units to collapse, 4 units to expand, and same way on the reciprocal end, 4 units and 4 units. So these, now notice, it's important. Oh, dang. No. It's important to notice that they overlap, and where they overlap, we begin here with the fundamental 1 over 2 oscillation and 2 over 1 oscillation. The overlap is 1 square unit here. Then when we go to 2, the overlap is, and that's 1 squared. And then the overlap goes to 2 squared, or 4. Then it's 3 squared, or 9, 4 squared, or 16. And then if we were able to show the fifth one, that would be 5 squared, or 25. So we really have a characteristic here of 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared built right in to our combination of ST units. I have to find my pointer again. Okay, so now what I've shown are the transitions of that pattern, which turn out to be the all-important n squared minus 1 pattern that is the basis of the Rydberg and the Balmer equations. So you see here where we then divide a space cycle by a time cycle, or vice versa. Can't remember how I designated them now, but that gives us 1 over 2 squared, or 4, the fundamental thing that Balmer found in this that corresponds to the fundamental ST unit. And then we go to the next one, which the equation, I didn't have enough room to actually show the equation here, but it would be 2 over 4 on the one end and 4 over 2 on the other end. And so that would be a, oh, I can't operate this well enough. This mouse requires me to click for the pointer, and then that changes. Anyway, so I can't show the equation, but if you look at the equation, you'll see then that it's the next cycle is 1 over 4 and 4 over 1, and you divide those, and that is equivalent to 1 over 16 or 1 over 4 squared. So we have 2 squared, 1 over 2 squared, 1 over 4 squared, 1 over 3 squared, 1 over 4 squared, and 1 over 5 squared, so on, which is the pattern, you notice, of Balmer's discovery and Redbird's rearrangement of his formula. And you can see this. This is called a quadratic polynomial. And it's n squared minus 1 is the polynomial, the basis of the polynomial. Anyway, so we can follow that same pattern that Balmer saw, because you see here 1 squared is 1 squared minus 1 is 0. So this level would be 0. But then the next level is 2 squared minus 1. 4 minus 1 is actually 3. And then the difference between the 0 level and this level 3 is, of course, 0 plus 3, or 3. So the n squared minus 1 value is 3. Then we go to the next one, and it's 3 squared. 3 squared. Ah, jeez. I'm sorry. I just can't do this right. 3 squared is 9, and minus the difference between 3 squared and 2 squared is 5. And then this level of 3 added to that difference of 5 is going to give you 8, right? And that is this n squared minus 1. And then the same thing with the others. So we get the same pattern where we go, and when we're looking at the differences between the n squared minus 1's levels, we get 0, 3, 8, 15, and 24. If you analyze Balmer's equations, that's exactly the pattern that he discovered. All right, now, bear with me. I am so frustrated by having to hold the mouse down and click it, and then anyway. So yeah, I hope you see that now. So if we then take those differences and multiply them by the constants, in this case we're going to use Redbirds constant, and multiply them by those, of course you can turn this around to get the minus for the admission spectrum, where this is, and invert it for Redbirds constant. It'd be 1 over 1 squared is 1 minus 1 over the level squared. So if we do that, we get Lyman's series, and I haven't shown them all here, but as many as I could. So if you go to the last one, it's 91.12 nanometers, and that going all the way down to the bottom is the wavelength that of the ionization potential, the limit they call it, of the electron within the proton. That's always important to understand. Okay, so but going from n squared, or if you want to 1 minus 1 over n squared times Redbirds constant, you'll get this difference here between, you'll go from 102.5 to 121.5. And that's a difference of 19 nanometers, 5 point. You can see the differences here of those. So the point is that it follows exactly from these relationships, which follow exactly from these relationships, which follow exactly from, hello, mouse, where did you go? From this relationship here, which follows from this relationship, which follows from well, I don't have it, but it follows from our ST units, the properties of our ST units. So that then we have one more slide to show how it works. You know how an ST unit is added to one of the three ST units of the electron. Notice that the electron has a charge of -3, which complements the charge of the proton combination of quarks and up quarks and down quarks, which equals a +3. So that and these are units of motion, not charge. Charge is considered to be -1 and +1, but it's made up of these three imbalanced ST units, all right? And it comes out exactly so that the difference in the unbalanced motion of the electron is the complement of the unbalanced motion in the proton exactly. And so if you change that, you would have that charge being changed, but it doesn't. It never changes, but the energy of the electron does change. And so we can see then by when we add the first ST unit, balanced ST unit, which is our fundamental, that then could be added to any one of these electron ST units, and that would be our first level. And then another one added to another ST unit, or maybe the same, but it's going to stay rather symmetrical. The laws of nature being as they are favor symmetry. So probably another one of these, it could be this one or this, it wouldn't matter which one, but we've selected this one to show the addition of the second ST unit with a value of 2 squared. And so that's like n is equal to 2. And of course, we get the lambda values that we've shown before out of each of these transitions. If we go from, we absorb it to come to the level 2 and then emit it again, we go back to level 1. Or emit level 1, we go back to the ground state of the electron. So in either case, the electron ground state is 18. The total motion of the electron ground state is 18 pipe 18. So when we add the first ST unit, that goes up by 4 again. So that's a total motion of 22 pipe 22. And then the next one is an addition of 4 more units of motion, which is 26 pipe 26. And then the next one, 34 more for 30 pipe 30. And we can go right on up to 46 pipe 46, which is the total motion of the proton, at which point the electron is totally ionized, and we are at 91.12 or whatever it is nanometers in terms of the wavelength, and the frequency then times Planck's constant is equal to 13.6 volts. The energy is equal to that. So anyway, it all works out really fine. And this again is the Lyman series. We could do the same thing for the Balmer series or the Paskin series, whatever, just doing the transitions from the levels indicated. For Balmer series, it would be from this level to this level, and all of them would be from a higher level, n higher than 3, to n equal to 2. Because that's the way he discovered it, because of the properties of numbers. So anyway, that's it. And of course, we have a few conclusions to wrap it up with. The first and most important one is that the work is preliminary. We think this works, but there may be a fatal flaw in it that we've overlooked, or some other thing that, because I do such stupid things sometimes, I can't believe it, and I get embarrassed by them, but at least I'm trying. That's the only thing that can consoles me. I've got to find a way to move forward with this, because I think it's a very important advance in our understanding of the physical universe, of the reality of the physical universe. But this work is very preliminary, very new. But as I said, all indications so far are that it's sound. As far as I can see, it follows, just like the other achievements, followed directly from the fundamental postulates, the two fundamental postulates of the reciprocal system of theory. Now that's important to understand because that's really our validity, right? Making sure that we are making correct conclusions, deducing correctly the implications, deducing correctly the consequences of the fundamental postulates at each step along the way. Then we look to see how reality, observation of reality, either confirms or doesn't confirm that deduction, that consequence that we have deduced from the postulates. And so far, they're really following right along the line of what has been observed in the laboratory. But of course, there's a long ways to go. This is a very new science. But with the important thing to understand about tonight's presentation, if this holds, this having been the foundation of the science of quantum mechanics, of quantum physics, this Bohr model and their ability to correctly calculate the energy levels of the Bohr model, and later we'll see of they fail at this a little bit, but we have an advantage of calculating the actual energy levels of the elements of the periodic table. So we move from the standard model to the periodic table with this breakthrough now. We'll be able to actually calculate the energy levels, not using the complicated quantum mechanical parameters of these orbiting electrons, where they have an angular momentum and a spin momentum, and then this level of energy determined by the radius of their orbit, and take all that into account, and then come up with the periodic table of elements on a basis of energy. And they've never been able to do it completely. They've only been able to do it in principle, they call it. But we have a better way of looking at that than they do. We know the periods are not 2n square as they have believed that they are, and so that doesn't fit the actual periodic table. But those periods are 4n square. Again, the number 4 being so crucial. So now that we have this ability to calculate the spectra, we are very confident that we can move forward with the calculations for the periodic table as we see it in what we call the wheel of motion. You can find that online. Just you can Google it. I don't think you need to use my name, but just Google wheel of motion and you can find that, or you can look for it on our site using our search function. But at any rate, you can find that periodic table, which explains a lot of how it is constructed as it is, as 4n squared. When n is 1, n is squared times 1, so 4 times 1 is 4. But when n goes to 2, then that's 4, and there's 16 elements. And then when n is 3, that's 9, there's 36 elements. And when n is 4, 16 times 4, that magic number 4, is 64 elements in the outer circle of the concentric circles that we call the wheel of motion. Well, at any rate, as I guess I say as the third bullet here, if this proves sound, if this new development, this new achievement number 7, proves sound with time, the implications of it are just profound, because by changing the atom, the model of the atom, we change everything else, not just the periodic table, the explanation of the periodic table, but it extends to the material slash cosmic two sectors, the two reciprocal sectors of the universe, which feed one another and therefore eliminate the need for the Big Bang and all the attendant problems that that has. Explains why the universe is expanding as it is, and also many, many other things that we will get into with time that Larson was able to illuminate to a great degree because of these two reciprocal sectors of the physical universe, one based on space and the other expansion, and the other based on time expansion. So anyway, this also indicates that Rydberg constant and its inverse may be the conventional space and time units that we need to understand in order to do a lot of our calculations. Because by using the natural units, it's just numbers, 1 over 2 or 2 over 1. But if we actually knew, like we do with the speed of light, what the actual number of meters per second is, then we would be able to do a lot more. So those are conventional. The speed of light is measured in meters per second, and that dimension is S over T has been shown by Xavier Borg to be the fundamental dimensions of the SI units. So if we can successfully convert between the conventional units and the natural units, whoa, man, that would simplify the physics tremendously. Well, so that concludes this historic, I hope, this historic presentation where for the first time we've presented the calculation of the atomic spectra using scalar mathematics and the reciprocal system of theory concepts. I hope it ends up being as satisfying to others as it has been for me. And so I'll bid you all good evening. Hope you have a good evening. Until next time, this is Doug Bundy bidding you adieu.